So we will start today with the second class of the chapter called solution. In the first class we had discussed about the basics of solution as well as the solution of gaseous in liquid, and obviously of course the solid solution. Now we are going to discuss mainly with or rather we'll start with the solution of solid in liquid. So first topic we are going to study today is that solution of solid in liquid and its vapor pressure. So solid in liquid, that's the common type of solution which you know, which we understand. For example, salt in water or sugar in water. But before going in further detail of this, we must understand first what is vapor pressure. Now suppose we have taken some amount of liquid, any kind of liquid, suppose pure water we have taken. So obviously some water molecules are at the surface of it. These surface molecules are going to get evaporated. If we cover it, the surface molecules are going to get evaporated. Now, till when obviously? The question is till when? It will get evaporated till the equilibrium is reached. So at equilibrium condition, these vapor molecules that is present on the top of the surface of the liquid is going to exert some amount of pressure, and that particular pressure is called vapor pressure. So what is vapor pressure? It's the pressure exerted by the vapor molecules that is evaporated from the surface of a liquid. Clear? Now, suppose we had taken a non-volatile solute in it. Suppose sugar, we added some sugar, same amount of water we had taken, and we added some sugar in it. So it is sugar plus water. Now, at the same condition means obviously the same temperature and the other conditions are also fixed. Okay, same surface area and so on. So now here the number of water molecules present will be lesser than the previous case, because there are some solute molecules, there are some sugar molecules that is also involved in it at the surface. But these sugar molecules are certainly not going to be evaporated because these are non-volatile. Yes? Okay. So the number of water molecules that is evaporated now is certainly less. So if the number of water molecules is less, evaporated water molecule is less, so the vapor pressure that will be exerted by this particular molecule, a particular solution, will be less than that of the pure solvent. So can we come to the conclusion that the vapor pressure of a pure solvent is always greater than that of the solution having the non-volatile solute in it? Means the solute is not contributing in the vapor pressure. Is it clear? Now, this one, the vapor pressure of the solvent in the pure solvent is generally represented as P1 naught. 1, we discussed already about this. 1 means solvent. But whenever we are writing naught means it's in the pure condition. There is no solution state. It's in the pure condition. And here the vapor pressure of the solution is because of the vapor pressure of the solvent only. So here the vapor pressure is represented by simply P1. Is it clear? Okay, fine. Now let's talk this graphically. Or before graphical representation, let us know that how the vapor pressure depends. What are the factors on which the vapor pressure depends? Now suppose I had taken water over here, and I have taken ether in another container of the same size. Some ether is taken. Ether means the nail polish remover, you know this, okay? Normally the nail polish remover. So if we take this, obviously the vapor pressure of the ether will be much more than the vapor pressure of the water. Why? Because the amount of evaporation is much more in case of ether, because it's a much more volatile liquid. Okay? So, can you conclude to the fact that the vapor pressure depends on the nature of the liquid? Nature of the liquid. Which liquid is it? Is it depending on that? Because depending on that only the evaporation depends. Now, Let us take water only. This is also water, this is also water. Suppose this we have taken at 25 degrees Celsius and we had increased the temperature to 35 degrees Celsius. So when you increase the temperature to 35 degrees Celsius, obviously more evaporation will take place. More evaporation takes place means the vapor pressure will increase. So does the vapor pressure depend on temperature also? With the increase in temperature, the vapor pressure of the liquid will also increase. So that's the second factor on which the vapor pressure depends, and that is what? That is temperature. That means the vapor pressure is depending on the nature of the liquid, or what liquid we are talking of, and it is also depending on what? It is also depending on the temperature. More the temperature, more is the vapor pressure. Is it clear? Okay, fine. So now we are going to go in the laws. The first thing we are going to study is now Raoult's law for Raoult's law for the vapor pressure of a solution, and Raoult's law. So we are going to start with vapor pressure of a solution and Raoult's law. Obviously, there are two types of solution. We are going to start with the first type, that is for the non-volatile solute. Non-volatile solute. That means the solute is not going to get evaporated. Fine. So we had already seen that if we take a pure solvent, whatever is its vapor pressure, and this is pure solvent, and if we take a solution, the vapor pressure of this is less. So this is vapor pressure P10 we know, and this is vapor pressure P1, and we know that the P10 is greater than P1 when the solute is non-volatile. Fine. Now let us do it graphically. Let us represent it graphically. So if we just plot, this particular graph is known as vapor pressure curve. We call it vapor pressure curve. So what we are doing, we are plotting the vapor pressure and temperature. Suppose at this particular temperature the solvent has got, the pure solvent, the water suppose, has got this much of vapor pressure. If we increase the temperature, what will happen to the vapor pressure? The vapor pressure will increase. So the vapor pressure is increasing, but obviously it is not increasing uniformly, it is increasing like this. So this is the vapor pressure of the pure solvent. Now, at the same temperature, in the solvent I added some solute, means I converted into solution. What will happen? Its vapor pressure at that temperature will be lessened. It will be less. Okay, fine. Now, this solution's temperature is increased. If we increase the temperature of the solution, its vapor pressure will also increase, but that will be always less than that of the pure solvent. So this particular curve is the curve for what? Is the curve for vapor pressure of the solution. This is the graphical representation of what? This is the graphical representation of the vapor pressure of the solution as well as the vapor pressure of the pure solvent. Whenever we are talking of solution, we are talking of the solution of non-volatile solute. Now what Raoult observed, it's very simple observation obviously. Suppose again I had taken some amount of water and we measured the vapor pressure. This is only water. We had measured the vapor pressure. Suppose the vapor pressure is 10. Now we have taken the same amount of water and added suppose 1 teaspoon of sugar to it. So obviously its vapor pressure will be lowered. Let the vapor pressure is lowered to 8. Now I had taken the same amount of water in another container and I had added 2 teaspoons of sugar. So obviously less number of solvent molecules are available at the surface. So the vapor pressure will be further less. So the vapor pressure is becoming suppose 6. So the vapor pressure of the solution depends on what? The vapor pressure of the solution depends on the fraction of the solute as well as the fraction of the solvent. If the fraction of the solvent is more, solvent means water. Fraction of the water is more, the vapor pressure is more. And that is what Raoult said. Raoult said that the vapor pressure of the solution, that is P1, is directly proportional to the mole fraction of the solvent. More the fraction of the solvent, more is the vapor pressure. It's simple. So from here, mathematically we can deduce some equation. So P1 is directly proportional to x1. So you can write P1 is equal to some constant into x1. Suppose k into x1. What is x1? x1 is the mole fraction of solvent. Now suppose we are putting some condition at x1 equal to 1. x1 equal to 1 means what? When we are talking of the pure solvent. Mole fraction of the solvent is 1, means mole fraction of the solute is 0. There is no solute present in it. Okay? So x1 equal to 1 means the vapor pressure is nothing but the vapor pressure of the pure solvent should be equal to k, because x1 equal to 1. So by putting this condition we got the value of k. Now this value of k we are putting in this equation, in the Raoult's laws equation, and what we are going to get is P1 equal to, in place of k we are now going to write P10 into x1. Fine? Okay. Now what we are going to do is just simple mathematical simplification. So can I write P1 divided by P10 equal to x1? Simple. Now what we are going to do is that we are going to subtract both sides from 1. So if we subtract both sides from 1, it is 1 minus P1 by P10 equal to 1 minus x1. Clear? Okay. So if we just further simplify it, can we write it as P10 is the LCM. This is P10 minus P1 equal to 1 minus x1, 1 minus x1. x1 is the mole fraction of the solvent. So 1 minus x1 is nothing but x2, that is mole fraction of the solute. So can I come to the equation of this? P10 minus P1 divided by P10 equal to x2. Now what is P10 minus P1? Let us come back to the graph. What is P10? P10 is the vapor pressure of the pure solvent. Suppose at any condition this is P10. Now what is P1? P1 is the vapor pressure of the solution. So at that particular condition means at that particular temperature the vapor pressure of the vapor pressure of the solution is this much. So it is lowered, it is decreased by this much amount. So this much amount is the decrease in vapor pressure. So P10 minus P1, that is the numerator of this equation, is nothing but the lowering of vapor pressure. We call it lowering of vapor pressure. Fine? Okay. Now when that numerator is divided by P10, means we are taking the ratio of it, we call it relative lowering of vapor pressure. Means the whole thing in the left hand side is called, or is just expressed as, relative lowering of vapor pressure. So from where we got this equation? We got this equation from nothing but this one. And this is what? This is the Raoult's law, the basic of Raoult's law. So the Raoult's law can also be expressed as the relative lowering of vapor pressure of a solution of non-volatile solute is equal to mole fraction of the solute. Is it clear? Now what is mole fraction? All of us know, and we can derive this from there. We can derive this, that we will come afterwards. That's the first type of solution we talked about. What was that? The non-volatile solute, solution of non-volatile solute. Okay. Now the second type we are going to study is the solution of the volatile solute. Now it's a little bit complicated. Now the solute is also volatile. Number B is for volatile solute. Volatile solute. Means the solute itself is volatile, and that also contributes to the vapor pressure. Suppose we are taking two components, component A and component B. Both are volatile. Let us take an example, water and alcohol. Suppose two liquids are we are taking, water and alcohol. Now both are what? Both are volatile. Now suppose we have taken some amount of A, then the vapor pressure for the A is because of A only. And obviously we are going to represent it by vapor pressure of A at its pure condition. When we take some amount of B only, then the vapor pressure that is represented by B is represented as PB naught. That's vapor pressure of B in its pure condition. Now which is greater? A is greater or B is greater? PA0 is greater or PB0 is greater? That depends on what? That depends on the nature of the liquid. That which is more volatile, whichever is more volatile, its vapor pressure is more. But when we mix A and B now, if we mix A and B, now here the vapor pressure is because of the evaporation of A as well as because of the evaporation of B. So it's the partial pressure of A plus partial pressure of B which is responsible, partial vapor pressure I mean, is responsible for the total vapor pressure. So you can write total vapor pressure. Total vapor pressure is equal to partial pressure of A or partial vapor pressure of A plus partial vapor pressure of B. Is it clear? Okay, fine. Now what Raoult said, Raoult observed about this type of solutions also, and very simply again he said, it's simple. Now suppose whenever we are mixing A and B, if the fraction of A in the mixture is greater than that of fraction of B, obviously the pressure that is contributed by A will be more than that of B. Or whatever is the fraction of A, it does depend on what? It does depend on, I mean the vapor pressure that is contribution of A, it depending on that only. That is what he told. He told that the vapor pressure of A in the solution is actually proportional to the mole fraction of A in the solution. So same way as previously we can write PA is equal to nothing but PA naught into XA as we had done in the previous case. And for B also same way we can say that PB equal to PB naught into XB. This is the Raoult's law for the lowering of, for the vapor pressure for the volatile solute. That the vapor pressure of the two components or vapor pressure of a particular component is directly proportional to its mole fraction, and this is the mathematical expression of it. Now let's just represent this graphically. Please understand it. Let's just represent it graphically. Okay. So here we are plotting in this direction, we are plotting mole fraction. In this direction we are plotting vapor pressure, and in this direction we are plotting mole fraction. In x-axis we are plotting mole fraction, and in y-axis we are plotting vapor pressure. Suppose at this point, the mole fraction of A is equal to 1. Means, what is the physical significance of this? That we are talking of pure A. There is no B. So mole fraction of B is equal to what? Mole fraction of B is equal to 0. So what is the vapor pressure at this condition? The vapor pressure at this condition is only the vapor pressure of A. That is the vapor pressure contribution of B is 0. So this is the vapor pressure of B. And what is the vapor pressure of A? This is the vapor pressure of A, and that is nothing but PA naught, because A is at pure condition. So we had taken actually what? Physically if we see that we had taken only A. Only A is there at this particular condition. Now in this we added little bit of B. Whenever we added little bit of B, the mole fraction of A decreased and mole fraction of B increased. So if the mole fraction of A decreases, the vapor pressure of A will also decrease. And if mole fraction of B increases, the vapor pressure of B will also increase. So mole fraction of, after certain conditions, suppose mole fraction of A is equal to 0.8 and mole fraction of B obviously will be equal to 0.2. So mole fraction of B is changing from 0 to 0.2, so its vapor pressure will increase. And mole fraction of A is changing from 1 to 0.8, so its vapor pressure will decrease. Like that. If we keep on adding B, one time will come, it will keep on decreasing, and one time will come when it will become equal to 0, means the vapor pressure of, at this particular condition, the mole fraction of A is equal to 0 and mole fraction of B is equal to 1, and this is the vapor pressure of B at pure condition. So this particular straight line, let us give some name, AB. AB is the vapor pressure curve for A. This is nothing but PA. Let us give some name to this, C and D. CD is the vapor pressure curve for B of the solution. Now let us ask you that what is the total vapor pressure at the condition when XA equal to 0.6, suppose. So XA equal to 0.6, suppose this one is the condition, XA equal to 0.6. So XA equal to 0.6, XA equal to 0.6 means XB equal to 0.4. At this condition, what is the total vapor pressure? So how can we get it? This much, suppose let us give some name, EF. EF is the vapor pressure, EF is what? EF is the vapor pressure of A, that is PA. Now let us expand it. EG. EG is the vapor pressure of what? Is the vapor pressure of B, that is PB. So what is the total vapor pressure? We know total vapor pressure is equal to PA plus PB. So total vapor pressure is EF plus EG, that is equal to PA plus PB, that is P total. So you have to calculate this vapor pressure, then this vapor pressure and calculate it. But we can avoid this by doing a simple geometry. Now if we join this A and D, we are going to get a straight line. This straight line is going to represent, the total vapor pressure, that is P. P total is equal to PA plus PB. Now if somebody asks you that what is the total vapor pressure when XA equal to 0.6, we don't have to calculate this. We can straight away calculate this. Suppose this is F, this is I. So EI is the total vapor pressure, which is nothing but EF plus EG. Is it clear? So this particular curve is representing what? This particular curve is representing the total vapor pressure curve. Now this solution of the volatile solute we talk is for the ideal solution. This is for the ideal solution. Okay, but it's not that every solution is becoming ideal. Most of the solutions are not becoming, not behaving ideal. This is not an ideal solution. Now, some solutions are deviating from its ideal behavior. When this solution of the volatile solute obeys a certain condition, we tell them ideal solution. What are these conditions? The first condition is that it must obey the Raoult's law, that is PA equal to XA into PA0, PB equal to XB into PB0. That's the first condition. Second condition is that delta H for mixing should be equal to 0. There should not be any delta H value for the mixing. Now, third condition is delta V for mixing should be also equal to 0. That means there is no volume change for the delta V is equal to 0. Delta V is equal to 0. Okay. So these are the conditions. If they are fulfilled by the solution of the volatile solute, then we call it the ideal solution. But if it deviates, now the deviation from the Raoult's law can be in two manners. So what is the manner? It should not be equal to, it should not be equal to, it should not be equal to, it should not be equal to. If this is the condition, then we are saying that it is deviating from the ideal behavior. Not equal to. Not equal to means what? Not equal to means either it is greater than or it is less than. So if everything is greater than, means PA is greater than XA into PA0, PB is greater than XB into PB0, delta H mixing is greater than 0, delta B mixing is greater than 0, then we say that the solution is behaving or deviating, I should say, in a positive manner from this ideal behavior. In that particular case, whatever PA is expected, we are going to find it out greater than that. This is the actual PA. This curve is actual PA curve for the non-ideal solution. Same way, whatever PB is expected, it is actually greater than this. And since PA and PB both are greater than the expected value, so the P total will be also greater than that of expected values. That is the positive deviation. That is positive deviation. Okay. Now negative deviation, another way it can deviate. Negative deviation. What is negative deviation? Negative deviation means these values should be always less than. That means PA is less than XA into PA0. PB is less than this. Delta H mixing is less than this. Delta B mixing is less than 0. And for that particular condition, always the value of PA or the value of PB or the total total P should be always less than the expected value. And obviously the nature of the curve will be like this. Like this, it is less than PB value, less than PA value, and obviously this will be also less than the total value. They will be all less than these values. Now the question is why that is happening. Why that is happening? Okay. Why some positive deviation? Why some negative deviation is taking place? So for the non-volatile solute we saw that it's normal. For the volatile solute it is three different conditions are there. For the ideal solutions, first is Raoult's law obviously, second is delta H mixing equal to 0, delta B mixing equal to 0. And when they are deviating from the non-ideal solution, it is non-ideal solution, it is either deviating in a positive manner or in a negative manner. Okay. Now the first question, that is why they are deviating in a positive manner, positive deviation. Why this is positive deviation? Positive deviation is because of positive deviation is because of that the interaction between AA and interaction between BB is higher than that in AB interaction. When the interaction between AA and the interaction between BB is greater than that of interaction between A and B, then they show the positive deviation. The most common example of this is the hexane and the ethanol. The most common example is hexane and ethanol. The mixture of N-hexane, normal hexane and ethanol. Same way, the negative deviation is just opposite. That means when the interaction between AA and BB is less than that of AB. When the interaction between AA and BB is less than AB, then they are showing what? They are showing the negative deviation. The most common example is the acetone and chloroform. Okay, so hope you understood what is positive deviation, what is negative deviation, and what is the logic for this. The logic for this is, for the positive deviation, the interaction between AA and interaction between BB is higher than interaction between AB. For the negative deviation, interaction between AA and interaction between BB is less than interaction between AB. Okay, the example of positive deviation is the N-hexane and ethanol, and the example for the negative deviation is acetone and chloroform. The interaction between the example for the negative deviation is acetone and chloroform. Okay, so that's all about the solution of the non-volatile solute and the volatile solute. The next term we are going to know is the azeotropic mixture, or we call it azeotrope, What is azeotropic mixture? Suppose we had taken two liquids, some amount of alcohol and some amount of water, and we had taken in a round bottom flask, and with the distillation system, in a distillation flask only. What is there? The alcohol is there and the water is there. Suppose the alcohol we have chosen is boiling at 60 degrees Celsius, and water normally is boiling at 100 degrees Celsius. Now if we increase the temperature of it, suppose the system is kept at 25 degrees Celsius. If we increase the temperature, when the temperature will reach to 60 degrees Celsius, only alcohol will get evaporated and it can be condensed further to there, and we can separate the alcohol and water. Water will boil at 100 degrees Celsius. That means the two liquids having the different boiling points, so we are going to two volatile substances having the different boiling point are going to boil in their different temperatures. Okay, but azeotropic mixture is such that it is behaving as an individual liquid. Means it is neither boiling at one component's boiling point or the other component's boiling point. It has a boiling point either less than the boiling point of both or greater than the boiling point of both. For example, suppose A is boiling at X, B is boiling at Y. When we take a fixed proportion mixture of A and B, this will either boil at greater than X and Y, or this will either boil at less than X and Y. If it boils greater than X and Y, we call it positive azeotrope, and if it boils at less than this, we call it negative azeotrope. Okay, so the positive azeotrope, or we also call it minimum boiling azeotrope and maximum boiling azeotrope. Now why some is showing the positive deviation or positive minimum boiling azeotrope? Minimum boiling azeotrope means what? Minimum boiling azeotrope means when the mixture is boiling at lower temperature than the individual components. Why it is happening? We must know the reason also. So first is positive boiling azeotrope. Positive boiling azeotrope is because positive boiling azeotrope, or better to say is that minimum boiling azeotrope, not positive boiling, minimum boiling azeotrope. This minimum boiling azeotrope is taken place because of positive deviation from the Raoult's law. This is the reason is what? The reason is the positive deviation. Reason is positive deviation. Let us just cite an example. Suppose H2O 5% and ethyl alcohol C2H5OH 95%. If we mix them together, they are going to form a minimum boiling azeotrope. How minimum boiling azeotrope? You know that this is boiling at 373 Kelvin. H2 is boiling at 373 Kelvin. C2H5OH is boiling at C2H5 that is boiling at 351.3 Kelvin. Okay, 351.3 Kelvin. That I have written again. Now H2 is boiling at 373 Kelvin, and this is boiling at 351.3 Kelvin. Individual. But when we mix this 5% and 95% solution, this solution boils at 351.1 Kelvin, which is less than the boiling point of both the components. You don't have to remember these values. No need of remembering these values. Only the concept has to be known. Okay, that what is minimum boiling azeotrope? What is minimum boiling azeotrope? When the boiling point of a solution, by mixing a specific amount of two components, is less than the individual boiling points, that particular solution called the minimum boiling azeotrope. Azeotrope means what? Azeotrope means a solution showing a different boiling point than the individual components. Either the boiling point of that solution will be higher than both of the components or less than. In this case it is less. And obviously the second type will be what? The second type will be maximum boiling azeotrope. Maximum boiling azeotrope. Maximum boiling azeotrope. Now when the maximum boiling azeotrope will be seen? The minimum boiling azeotrope is seen when the deviation is in the positive manner. It is deviating in Raoult's law in the positive manner. And if it deviates in a negative manner, that is going to show the maximum boiling azeotrope. So maximum boiling azeotrope is shown to those solutions where it is deviating in a positive manner. Okay. For example, H2O 100%, 80% and HCl 100%, 20%. H2O and HCl. H2O 80% and HCl 20%. Now, you know H2O is boiling at 373 Kelvin and HCl is boiling at HCl is boiling at 188 Kelvin. 188 Kelvin. But when you mix this mixture in this proportion, the mixture is boiling at 383 Kelvin, which is greater than the boiling point of both. So this is a kind of mixture which is showing what? Which is showing the maximum boiling azeotrope. Maximum boiling azeotrope means what then? What is maximum boiling azeotrope? When the azeotropic mixture boils, at a higher temperature than the individual components. What is the example? The example is this. Again I am saying no need of remembering this example and these values. You must only know that what is maximum boiling azeotrope, what is minimum boiling azeotrope, and why are they showing this behavior. Why are they showing minimum boiling azeotrope is shown because of the positive deviation from the Raoult's law. Maximum boiling azeotrope is shown because of the negative deviation of the Raoult's law. So that's all about the volatile solute. Next class, we are going to enter in the most important topic of this particular chapter, which is called the colligative properties. Obviously, we are going to start in the next class, colligative properties. And we are going to start it in the next class. For this, colligative properties. Okay. So, till then, I am signing off. Going to meet in the next class. Thank you.